There's a paper out that's really challenging how we think about AI development. It basically argues that we've all been so focused on these tiny, incremental gains that we're completely missing the real story, a massive exponential leap in AI capabilities that our current benchmarks just aren't designed to see.
So with billions of dollars pouring into large language models, everyone's asking the big question: are we hitting a wall? Are we finally seeing diminishing returns? Well, this paper argues that the answer is resounding no, but the reason why is probably not what you're thinking.
So here's how we're going to break it down. We're going to start with this so-called illusion of diminishing returns. Then we'll dive into a really weird puzzle about how these models behave, look at a simple test that gets to the bottom of it, and then uncover something called the self-conditioning effect, which honestly might just reframe this whole conversation. All right, let's jump right into the paper's first big idea. And it's a bit of a counterintuitive one. It really makes you rethink the connection between small improvements in AI models and what they can actually do in the real world. Okay, so take a look at this graph. This visual is pretty much the key to the whole argument. On the bottom, you've got single-step accuracy, how often a model gets one simple thing right. On the side, you've got task length, how many of those simple things it can do in a row. Now look at that blue curve. It's not a straight line. Once you pass a certain accuracy threshold, even a tiny little improvement leads to this huge exponential explosion in how long of a task the model can actually finish. And that leads to the author's main point. Maybe we're all measuring the wrong thing. The true value of an AI agent isn't about acing a single question trivia test. No, the real economic game changer is its ability to handle long, multi-step projects. That's where you see this compounding exponential growth, not the slow linear progress we thought we were getting. And that insight brings us to a really fascinating puzzle that the paper digs into. A weird paradox that you see in even the most powerful AI models out there today. This is the thing that has been driving researchers nuts. We have these models that are brilliant, right? They can solve complex logic puzzles, write code, compose poetry, but then you ask them to do something incredibly simple over and over and over again, and they just fall apart. It's like a genius mathematician who suddenly forgets how to count to 20. What is going on? The paper proposes a really important distinction here. The problem might not be with the model's high-level planning or its ability to reason. The models seem to know what they're supposed to do. The hypothesis is that the failure is happening at a much more basic level: execution. Just flawlessly carrying out the instructions, step after step after step. So if that's your theory, how do you prove it? Well, the researchers had to get clever. They needed to design an experiment that could totally separate the model's ability to plan from its ability to just do what it's told. The goal here was beautifully simple. They wanted to create a task that requires zero planning, none. The model gets all the info it needs, it gets the full plan right up front. Its only job is to follow the instructions perfectly for as long as it can. And this is the task they built. It's called Retrieve Then Compose. It's dead simple. The model gets a list of words and numbers. In each turn, it has to look up a word, get its number, and then add that number to a running total. That's it. No creativity, no reasoning, just pure, repetitive execution. The results were, frankly, stunning. Even the models that were perfect on step 1, 100% accurate, they all inevitably started making mistakes as the task stretched on. Their performance just completely collapsed. This was the proof. Just doing something for a long time is itself a fundamental and seriously underestimated challenge for these AIs. So, we know they fail. But why do they fail? This question leads us right to the heart of the paper's biggest discovery, a phenomenon that they call the self-conditioning effect. Now, the simple answer would just be, well, a tiny error rate is bound to catch up with you over hundreds of steps. But the data showed something much stranger. The model's error rate wasn't constant. It was actually getting worse as it went along. Why would that happen? And here is the answer. It's because every time the model generates an answer, that answer, right or wrong, becomes part of the context for the next step. So when it makes a mistake, it's essentially polluting its own short-term memory. It then looks back at its own error-filled history to figure out what to do next, which makes it even more likely to make another mistake. It's a vicious downward spiral. And this graph is basically the smoking gun. To test this theory, the researchers intentionally fed the models a history that was filled with errors. The green bars show the model's accuracy when its history is perfect. The red bars? That's the accuracy when half of the history is just wrong. The performance absolutely tanks. It's clear evidence that the models are being negatively influenced by their own past mistakes.
Okay, so if that's the problem, this downward spiral of errors, what on earth is the solution? Well, this is where the paper connects everything to the latest generation of AI models, the ones that are being trained to actually think.
The fix, it turns out, is to get the models to reason things out before they spit out an answer, using techniques like chain of thought, where you prompt the model to talk through its process step by step. That process is what seems to break the cycle of self-conditioning. And this quote, straight from the paper, says it all. When they ran these tests on models that were specifically fine-tuned to think out loud to generate these reasoning steps, they found that these models were basically immune to the problem. The negative feedback loop was gone. So why does this work so well? Well, there are two main reasons. First, it changes the model's goal from just predict the next most probable word to actually solve the problem correctly. Second, the researchers found that when these models think, they basically ignore the messy history and focus entirely on the current step, giving them a fresh start every single time.
Okay, so let's tie all of this together. What does this discovery really mean for the state of AI today and for how we should be measuring its progress from now on?
This final benchmark from the paper just lays it all bare. It shows how many of those simple retrieve then compose steps different models could handle. The non-thinking models, they're in white, they top out after just a few steps. You see some improvement with basic chain of thought prompting, but then look at the models in black, the ones specifically trained to think. They are playing a completely different sport. The capability gap is just enormous.
And that is the real takeaway here. If we start measuring AI not by single-shot questions, but by its ability to perform long, multi-step tasks, then a whole new frontier of capability opens up. And on that frontier, progress isn't stalling out or diminishing at all. In fact, it's accelerating.
Which brings us all the way back to that very first exponential curve we looked at. This incredible leap in capability, going from a handful of steps to thousands, all comes from what look like tiny marginal gains in single-step accuracy. And that leaves us with a pretty wild question to think about. If this is what we get from just a few more points of accuracy, what happens when we get the next few points?